Welcome to Smooth Muscle Contraction. In today's video, we'll be looking at the proteins involved in phasic and tonic contraction. The first protein we're going to look at is called calmodulin. Once the cell has experienced an increase in intracellular calcium levels, we're going to see 4 calcium ions bind to each of calmodulin's high-affinity binding sites. This causes calmodulin to change shape and take its active form. We'll now introduce our second protein, myosin light chain kinase. You might also know it by its initials, MLCK. Our calmodulin is going to move over and bind to MLCK, causing it to activate. Thus empowered, our MLCK can swim away until it finds our contractile proteins, actin and myosin. These should look similar to the proteins we saw in skeletal muscle, but there's a big difference. On its own, the myosin in smooth muscle is unable to bind with actin. This is where our MLCK comes to the rescue. Using a molecule of ATP, it's going to add a phosphate onto our myosin, shown here as a blue P. With this extra phosphate attached, our myosin can now bind to the actin filament. This produces energy, which is then released as heat, and also captured by the red phosphate, breaking its bond. Removing the phosphate allows myosin to contract from a high-energy state down into a low-energy state. The myosin will stay connected to actin until an ATP comes along and binds to the myosin head. The myosin is now able to break the ATP into an ADP and a phosphate. The energy released from breaking this bond cocks the myosin into a high-energy state, kind of like pulling back on a spring or a catapult. With our special blue phosphate still attached, our myosin is able to rebind with actin and start contraction again. Please note that although I've shown actin as being stationary, in a real cell we'd actually see our myosin staying put and pulling the actin towards it, kind of like in a tug of war. In the meantime, our actin finishes up another power stroke cycle and... What in the blue blazes was that? That, my friends, was a myosin light chain phosphatase, otherwise known as MLCP. While the P in MLCP doesn't technically stand for Pac-Man, I wouldn't be offended if you imagined it that way. It's an important regulatory enzyme for smooth muscle, and its favorite thing to do is to clip the special blue phosphate right off of our myosin. Without our phosphate, contraction stops until another MLCK comes along. Alright, here we go again. Now we can start to contract as long as... Oh, darn it! MLCP did it again! Well, I guess we'll just have to add another phosphate so we can keep contracting. Boy, I sure hope that MLCP will leave us alone for a little bit longer, because we're starting to go through a lot of ATP. He did it again! Okay, so... obviously, if we're going to get this contraction to go anywhere, we're going to have to find some way to get MLCP to calm down a little bit. Thankfully, our cell has just the solution. Rho kinase. As a kinase, its job is to phosphorylate things. Our Rho kinase's target is going to be our good old MLCP. Ha! That ought to shut him up for a little bit. With MLCP inactivated, we can finally enjoy some uninterrupted muscle contraction. Now, we don't want the smooth muscle contraction to go on forever because, well, that would literally be gut-wrenching. Now's probably a good time to let our friend MLCP come back. To do that, we're going to use some cell signaling to inactivate our Rho kinase. With Rho kinase out of the way, our MLCP can break free and go back to doing what it does best. This stops the contraction process and our smooth muscle is able to relax. Up to this point, everything we've seen is dependent on the ratio of MLCP to MLCK. If we have lots of active MLCK and mostly inactivated MLCP, then our myosin stays phosphorylated and we have phasic contraction. This is the kind of contraction you'd see in peristalsis, basically contraction followed by relaxation. What would happen though if we were to tip our ratio and end up with lots of active MLCP and relatively little MLCK? Well, with so much extra MLCP, it's basically going to get so excited that instead of waiting for the myosin to release to clip off the phosphate, it's just going to go right for it and clip off that little blue phosphate while the myosin's still attached to the actin. So, what happens now? Well, our red phosphate and ADP are still going to detach, and our myosin's still going to contract, and the ATP is still going to come and bind to the myosin, but our myosin actually stays stuck on the actin. It can't let go. We call this stuck phase the latch state. The latch state can persist for hours, with our myosin trying to get loose. While it takes a long time, eventually it will be able to break free. The latch state actually gives a huge advantage to smooth muscle. If you think about it, the latch state allows our smooth muscle to contract and then hold that contraction for hours without having to use any extra ATP. The whole time that our myosin and actin are in the latch state, they're holding that contraction. This is important for muscles that need to be able to hold a contraction for long periods of time without getting tired or using up a lot of ATP. If you're having a hard time thinking of examples of where this would be useful, just think about, maybe the muscles that hold your bladder closed? We call this style of contraction tonic contraction. And with that, there you have it, folks. You have your phasic contraction, which allows you to contract and relax within a relatively short period of time. And then you have your tonic contraction, which allows a muscle to contract and then hold that contraction for hours.